Hello. In this lesson, we're going to talk about accuracy as compared to precision, and then we'll learn a little bit about calculations involving measured quantities, where we need to pay attention to the number of significant digits that are involved. You've got your guided student notes ready? Let's get started by looking at the difference between accuracy and precision. In casual language, people tend to use accuracy and precision interchangeably, but the truth of the matter is that they have different meanings, and it's important for us to know what the words mean, because when we communicate with people, we want others to see us as educated professionals in our field. So we make sure that we use precise language and good vocabulary. Let's get started here. Accuracy describes how close a measured value is to the true value. If you measure something and claim that it is 2 inches long, that's what you say. But 2 inches is not going to be the exact length of something. The actual exact length, down to as many decimal places that you may want, is completely different from 2 inches that you said. So that's accuracy. It says how far away is what you said from what the actual result actually is. All right, anyway. Precision is different. Accuracy talks about how close a single value is to the truth. Precision talks about a set of values. Precision is concerned about whether or not results are repeatable. So precision describes how close repeated measurements are to each other. All right, so it's probably better if we have some pictures. So here we have some bullseyes, and the little blue dots represent the measurements, and the very center of the bullseye is the truth. So when we look over here on the left, we have a really nice grouping, but it's nowhere close to the center. This nice grouping means that we are precise. Hang on, let's fix that. Okay, I think I've got it fixed. At any rate, we have this nice little grouping over here, and this means that things are precise, because all of the results are close together. But they're nowhere close to the center, so these are not accurate. My mother used to do this thing with a scale where she would set it to be 5 pounds heavier than it actually was. So this is sort of that idea. The scale would give consistent readings, but they would be far away from the truth because that's the way that she had set it. Over here on the upper right-hand side, we have a lot of values that are really close to the center, but they're pretty spread out. Being close to the truth, being close to that center, makes us accurate. But being spread out means we are not precise. On the lower left, we've got a mess. These are not all close to the center, and they're also not together. This is what might happen if we were on a road trip and somebody said, hey, how many hours is it going to take us to get there? And I just took a die and rolled it, and whatever the number was would be the number of hours I would say. So if the road trip was actually going to take 2 hours, this little dot here would have been close to the truth by accident. And all of these are just crazy. So it's not anything that's repeatable. This is not precise and is also not accurate. The reason why people use precision and accuracy interchangeable is because we want both. We expect both. We have a lot of situations in which we get both. A nice cluster here in the middle, everything is close together, and everything is close to the truth. So this is the picture that is precise and accurate. All right, so there's the difference between accuracy and precision. A while ago, we talked about tolerance. And tolerance actually describes an amount of inaccuracy that's allowed. Remember, accuracy talks about how far you are away from the truth. So when we say we have a tolerance, that says how far away from the truth can you be, and it's still all right. And then finally, before we flip the page, we want to talk about exact values. With exact values, there is no uncertainty associated with the value. There is no uncertainty. When you open up a brand new carton of eggs, you expect to see 12 eggs, and 12 eggs there are. That's it. Nobody's going to count them any differently. There is no uncertainty associated with the value. 12 eggs make a dozen. And not only that, but you haven't rounded a thing. You could report that 12 is 12.00000 with infinitely many zeros, and it would still be exactly correct and perfect. No part of the value has been rounded. We never say that there are about 12 eggs in a dozen. There are 12 eggs in a dozen. So no part of the value has been rounded. All right, let's flip the page and see what's coming up next. Ah, look at that, just a little bit more vocabulary. So we had exact values. Measured values are different. So things that you count are exact. Things that you measure with some sort of device will always involve approximation. We have a lot of digital measuring devices in our world now, but they are still things that are approximating. They can only tell you down to a few decimal places how big something is. They can't give you infinitely many decimal places like an exact value can. So measured values involve approximation. They all have a limited number of reliable digits. They have a limited number of reliable digits. When we talk about the precision of a measuring instrument, this means what is this tiniest amount, the smallest change that the instrument can detect. It is the smallest notice, oh my goodness, my tongue has stopped working. The smallest noticeable increment. So every measuring instrument, no matter how precise it is, has some error associated with its results. We define this as the greatest possible error of a measurement, and it's pretty easy to calculate. It's just half the precision of the measurement. So let's see what we mean here. Let's go to the track. Judith has a stopwatch. Emil is running. Emil runs the 100-meter dash in 12.3 seconds, according to Judith's stopwatch. We know that that is not exactly the truth out to an infinite number of decimal places. There's some rounding error in there. There's also probably a little bit of operating error in there for when you clicked and unclicked the stopwatch. But at any rate, we'll just ignore the operating error for just now. What is this stopwatch doing? Well, right here is the far right digit in the tenths place. So the precision of this instrument is the nearest tenth of a second. That's the smallest difference that the stopwatch can register. What was Emil's actual time? Well, we don't know. What we do know is the bounds on it. When the stopwatch registers 12.3 seconds, what it's actually saying is that the truth is stuck between, or is one of the possibilities of things that actually rounds to 12.3 seconds. So Emil's actual time could have been as low as 12.25 seconds. That would have rounded to 12.3. It also could have been as high as 12.35. We'll keep a strict inequality here because you know the 5 is going to push that 3 up to a 4, but we'll put an equals down here because the 5 does round things up to the 3. And there you have it. The truth is somewhere between 12.25 seconds and 12.35 seconds. The greatest possible error is 1/2 of the precision, which is 0.05. And that, of course, is the difference between this edge and the middle that was reported. Okay, that's pretty much it. Precision, the actual, and the greatest possible error are all related, and figuring them out is pretty straightforward. Pause the recording and you try example 2 on your own. Come back when you're ready. All right, so Frances is watching this race as well, and she has a more precise stopwatch. Hers is precise to the 1/100th of a second. And this means that she has figured out the actual time is somewhere, something that rounds to 12.27. 12.275, if we were just a little bit below that, would round to 12.27, and 12.265 would round up to 12.27. Now you can see that this interval here is much tighter than it was before, and that's what being more precise is all about. The greatest possible error is half of the 1/100th of a second, 0.005, the distance between the reported value and the farthest value that would round to that number. If we're working on a ruler, a US ruler that was measuring in inches, we would have different types of subdivisions. They would be fractions or fractional. So this ruler has subdivisions of 1/16 of an inch. We use the smallest subdivision possible. That's our precision. The greatest possible error is still half of that. And hopefully you remember how to how to multiply fractions, and you know that that's worth 1/32 of an inch. All right, so let's flip the page and talk a little bit about significant digits. We use significant digits to communicate with other people about the precision of the measurement. So significant digits convey information. about the precision of a measurement. So the first thing we do is look at a measurement and decide which digits are significant and which digits are not. And the rules for the most part are pretty easy. If it's not a 0, it's definitely significant. We wrote that number down on purpose. Zeros are where we have to be careful. Any 0 that's used as a placeholder is not significant. It's just something you had to put in so that the other digits were in the right spots. If you intentionally put a 0 down, other than as a placeholder, then that 0 is significant. So the idea is that in number A here, this 0 is in the middle and this 0 is in the middle. Both of these are significant because they're not at the beginning or the end of a number. This value would have 1, 2, 3, 4, 5 significant digits. The second one here only has 2, right there. The other zeros are just placeholders. And the one down here, well, what do you think? Yes, that has 5. The 0 in the middle doesn't matter. So 1, 2, 3, 4, 5. Also 5 significant digits. The problem comes when we're working with whole numbers, large whole numbers that end in zeros. It's sometimes kind of hard to tell which of the zeros are significant and which of the zeros are not. One thing that we can do is rely upon our knowledge of the situation. You can imagine if a 0 was replaced by a 1, is it a measurement that you would possibly obtain in the same situation? For example, if you went down and you looked at the reading on your water meter and you saw 81,000 cubic feet of water had been used, would it be sensible for you to look at the water meter in a little while and see 81,001 cubic feet? Could you do this? And would you see a reading like that? And the answer is yes, you would. Since you would see a reading like that, well, just imagining that 1, it's not really there, then all of these zeros are significant. So this one has 5 significant digits because 81,001 would also be displayed. Your water meter can read down to the nearest whole cubic foot. It doesn't count by thousands at your house. If we were talking about the population of a city, however, that's a whole other story. We don't generally tend to know down to the single person how many people are in a city. Even if we were doing a census, we wouldn't know this thing. This is a rounded value. It's been estimated. It's approximated. Approximated to where? Well, we could talk about that. Not to the nearest whole number, probably not down to even the nearest 10. So it's possible this is to the nearest 1,000 or to the nearest 100. So we would say maybe 2 or 3 significant digits. That rounding to the nearest 100 or the nearest 1,000 is sensible. Well, we have to pick one. Do we want 2 significant digits or do we want 3 significant digits? And since we really don't know what happened in this city, we're not sure. So if we're ever in doubt, we are not going to count the zeros on the end of a whole number. So this says do not count the zeros on the end of the whole number, which means that 81,000 would have 2 significant digits. Now, in technical fields, we have to be able to tell people how many significant digits we have. We can't just go around deciding that the zeros count or the zeros don't count depending upon how we're feeling that day. So what do people do? And there are a couple of options. One thing that happens, hang on, there, that's better. One thing that happens is that people underline a zero if it's significant, or at least the far right zero of all the significant digits. So let's look at this idea of 81,000 again. And let's imagine a couple of different scenarios. Here, 81,000 with the zero in the hundreds place underlined would contain 3 significant digits, all of those. And that would tell us that this number was rounded to the nearest 100. Another option is to actually write down how many significant digits you have. So maybe we want to tell people that this 81,000 actually contains 2 significant figures. This F is for figures. They don't tend to call them FDs. They use SF for significant figures. At any rate, that would tell you that only these count. It doesn't matter what digits they are, those are the ones that count. It specifically says we have 2 significant digits. And in this case, the 81,000 was rounded to the nearest 1,000. If we went back up to this one again and thought that this 0 was underlined, then we would have 4 significant digits, and the value would have been rounded to the nearest 10. The last thing we can do in a technical field is to use scientific notation. Well, yeah, it's science, it's technology, it's a technical field. They go together. If you want this 0 here to be highlighted as important, then scientific notation allows us to do that. We write down everything that matters in scientific notation. This one would have 3 significant digits because every digit in the coefficient of a number, so the coefficient is this part. If you write the digits down in the coefficient, they matter. Well, it's that easy. We don't have to worry about what matters and what doesn't. Okay, so how do we do arithmetic with measured quantities? You'd think we'd do it the same way that we have been doing it, but the truth of the matter is we've been doing it without paying attention to the details until now. When you have a measured quantity, there's always some error, and adding or subtracting to it sometimes makes a difference and sometimes doesn't. So imagine, for example, that we're talking about Donald Trump. At one time, somebody reported his net worth as being $3.9 billion. Donald Trump could walk down the street and drop a quarter, and he would never notice. You and I might notice. Might be my last quarter. Donald Trump could go to a restaurant and leave a waitress $1 million tip. $1 million tip! And it wouldn't change how people reported his net worth. $1 million is so small compared to 3.9 billion that leaving that sort of tip at a restaurant wouldn't change a thing. So sometimes adding or subtracting amounts just doesn't matter. So here's what we do. So that we don't report insignificant figures, we have some special rounding rules. The rules are different if we're adding and subtracting than if we are multiplying or dividing. So let's take a look at these. Remember, these are for measurements, not for exact values like counts. You can still add 5 apples and 13 apples and end up with 18 apples. But 5 inches and 13 inches and 3.5 inches might give you a little bit of a different result if we were careful about the rules. So let's give it a shot here. What it says is that the first thing we're going to do is make sure we're all working with the same unit, because of course to add things we have to have like units, just like we have like terms and like fractions. And then after that, we want to round the result so that it has the same precision as the least precise measurement. So the first thing we're going to do is just follow the rules, watch what happens, and then we'll get into a little bit more detail here. I'm going to use, let's try just grams. So we have 375.7 grams. 58 centigrams, well, centi means 1/100th, So we'll move this decimal point 2 spaces to the left. That will be 0.58 grams. And then we also have 254 milligrams. Remember that milli means 1/1000th, 10 to the negative third power. Move the decimal 3 spaces to the left. This is 0.254. And then we need to add them all together. And everything is now in grams. So when we add these together, we get, let's see, 4, 3, 5, right, carry the 1, yep, and then 5, 7, 3. We think we have that number of grams, but we don't. Don't get fooled into thinking just because you see a bunch of digits that they all count. They do not all count. Here's what really happened. Whoever gave us this first number was rounding to the nearest tenth of a gram. Right, this could have been anywhere between 375.65 grams and 375.75 grams. That's why we were talking about precision and the greatest error before. So what's really going on is this. We have 375.7, 7 in the tenths place, and that's questionable, right? That may or may not have been rounded up. It could have been a 6, depending on what's here, which we don't know. And we also don't know what's sitting in the thousandths place. These 0.58 grams, we have a decimal point, there's a 5, there's an 8. The 8 is questionable because it could have been rounded, and we have no idea what was in the thousandths place. And then we wanted to add on the 0.254 grams, and this 4 was questionable because we don't know the digits to the right of it. So you see, it looks like these are nice exact numbers, but it's not true. There's a lot of stuff that we don't know. How do you add these together? How do you add question mark plus 4? I mean, you know, let's try this here. Let's put our digits back down. 375.534. This 3 and the 4 here on the end are completely unreliable. There's way too many question marks associated with it. This 5 is still a little bit questionable, but we can keep it. Right? It's just a little questionable, not a lot. These 3 and the 4, we have no idea that those are really there at all, because there's too many question marks that could have been added in. So in all fairness to the people that were measuring things for us, we can really only say that when we add up all of these, we get something that is about 375. Whoops, I can't add, can I? That should be 376. Let me fix that. I got so busy adding, I forgot to carry the 1. Well, anyway, 376.5, and that's really as far as we can go. Grams. Okay, so that's why the rule is the way it is. This 4, completely not helpful at all, because it's being added to too many unknown numbers. We don't know that there's really a 4 there. And so we don't report it if we're not at least sort of sure that it should be there. All right, let's flip the page here and try a couple more. The rules for multiplying and dividing are a little bit different. The first thing that we're going to do is, just like we did before, save all of the rounding until the very end. We've been doing this throughout many of our lessons, making sure that we don't compound error by rounding in the middle of our calculations. But when we get all done, after we've multiplied or divided measured quantities, we want to round the result so that it has the same number of significant digits as the measurement that has the fewest significant digits. So this is not decimal places like we had before. We're just going to count significant digits. So let's see what happens here. We have an object that weighs 327,000 pounds and has a volume of 123.8 cubic feet. We'd like to calculate the density of the object. We know that 327,000 pounds is a rounded value. We know that 123.8 cubic feet is a rounded value. Nobody could know either of those values out to an infinite number of decimal places. So here we go. Let's just divide 327,000 divided by 123.8 and see what we get. All right, this long thing times 10 to the third. So let's redo that. That will be 2, move the decimal point 3 spaces to the right, 641.357.027, and you know that there are more digits after that. And the question is, how many of these can we keep? I mean, really, this object we were rounding to the nearest 1,000 pounds before. So we wouldn't have any right at all to start claiming these types of decimal places in the answer. Don't be fooled just because your calculator shows you digits. Don't let it tell you that they all matter. Let's see, the numerator. The numerator has how many significant digits? Well, these zeros here don't count. So we have 327, that's just 3 significant digits. The denominator contains 4. There aren't any zeros at all, so we just count all the digits. And the rule says we want to round so that we keep the fewest number of significant digits. So we're going to round the result so that we keep 3 significant digits. And that means this many right there. So we would say that this object's density is approximately 2,640 pounds per cubic foot. And we would never even think about reporting all of those decimal places to the right. Okay, let's slide down and try another one here. The insulation in the walls of a refrigerator is made of styrofoam sheeting. Each wall measures 0.53 meters by 1.60 meters. How many square meters of sheeting do we need for 6 walls? Remember, we're not going to round until the very end. And the first thing we're going to do is just set up this calculation. You know that to find the area of a rectangle, we have to multiply the length times the width. So we would take 0.53 and multiply by 1.60. Right, that digit in the hundredths place is there on purpose, just like this digit here in the hundredths place is there on purpose. We're not just going to leave it off and be sloppy about things. And then that would give us the area, and of course we would have to multiply this by 6 because we want 6 walls. And I want to keep that one in red on purpose. Oops, there, now it's red. Because the 6 is different. The 6 is not a measured quantity. The 53 is measured. That's our first factor. It has 2 significant digits. Remember, this 0 here out front doesn't count. The second factor has 3 significant digits. The 1, the 6, and the 0 all count. But the third factor is not measured at all. This is exact. We want exactly 6 walls. Not about 6 walls. This is an exact number. And what that means is that it does not influence the number of significant digits that we need. The fact that 6 only has 1 digit in it isn't going to matter because it's not a measured value. All right, so let's do the calculation and see what we get. 0.53 times 1.60, if you like, multiplied by 6 gives us 5.088. It appears that I have left my calculator in scientific notation mode, but that's okay. It's good for you to see it. 5.088 square meters of styrofoam sheeting. How many significant figures are we going to keep? Well, we want to keep the one that's got the smallest number of significant figures. So there we go. We're going to use 2 of them. And that would mean we would need approximately 5.1. We round so that we have kept 2 significant figures. All right, this last one is for you. It shouldn't take very long. The idea is to calculate the area of a circle. You know that the area of a circle is pi times the radius squared. Pi is an exact number. All right, we haven't rounded it in any way. So that's your job. Pause the recording, come back when you're done. And hopefully your work looks something like this. Pi times the radius squared. Of course, you used your calculator and came up with this number that has lots and lots and lots of digits. But since the radius is a measured quantity, we can't count on these digits way over here on the right as being reliable. The question is, how many digits should we keep? And that means we want to look at this radius measurement and say, how many significant digits does it have? And it has 4. And of course, we used 4 significant digits for each factor because they were the same. So we want to keep 4 significant digits. This much. We want to round there. So the area of the circle is approximately 287. This 4 will round to a 5 because the digit to the right of it is a 7. But after that, we will have some placeholders. And the units are inches squared. There we go. That's how significant figures work. Be careful, refer back to the rules often, and we'll talk to you later. Take care. Bye-bye.